Okay, let's get started. Welcome everyone. Welcome to our Climate Change AI webinar series. My name is Shafat. I am a volunteer at Climate Change AI. I work on the tutorials team where I facilitate the development of tutorials, much like the one that is going to be presented today. Before we dive into our webinar today, I want to take the opportunity to provide a brief introduction to Climate Change AI. For those that are attending our first event, Climate Change AI is an initiative that fosters impactful work at the intersection of climate change and machine learning. We provide educational tools and infrastructure. We provide community building, and our goal is to advance discourse in the area. CCI conducts various initiatives to disseminate knowledge at the intersection of climate change and AI. We offer both digital resources and in-person meetups in the form of summer schools, conferences, webinars, workshops, and meetups. We provide grants to support projects around the world. We are also actively engaged in policy conversations. And in addition to that, we bring together a very vibrant community of people and one of the ways we do that is through our community platform. So you can go to community.climatechange.ai and join our platform, and make valuable connections with people interested in various fields within the area. You can also go to climatechange.ai/blog. Our blog is an invaluable resource. We upload regular blog posts where our team members provide insights and behind the scenes on some of the projects we are running, as well as interesting articles on climate change and AI research and industry applications. You can also sign up to our newsletter. Our newsletter goes out to a broad range of audience, and we generally provide updates on different kinds of funding opportunities, conference submission calls, and job opportunities and relevant readings within the field through our newsletter. So before I introduce our speakers today, I'll give you an overview of how the presentation is going to work today. So there will be 45-minute talk, and after the talk, we have 15 minutes reserved for Q&A. So throughout the talk, you can go to the Slido link that is on the screen right now and also in the Zoom chat. You can go to the Slido link, enter your questions, and upvote other people's questions. At the end of the 45 minutes, we are going to prioritize questions that have been upvoted the most and ask those questions to our speakers. All right, so without further ado, we have the pleasure of having Feline Baumer and Anna Hedstrom as our speakers today. Feline received her bachelor's and master's in physics at the University of Heidelberg. Following her graduation in 2020, she started pursuing her PhD at the Department of Machine Learning at TU Berlin in October 2022, with a focus on explainable artificial intelligence and applications in the field of climate science. Currently, she is part of the UMI Lab research group and is continuing her PhD at the Department of Data Science in Bioeconomy at ATB Potsdam. Anna is currently pursuing her PhD and is part of the independent research group, Understandable Machine Learning, UMI Lab, focusing on explainable AI and interpretability topics. She received her master's degree in the machine learning at the Royal Institute of Technology, KTH, and her bachelor's degree at University College London. Her current research interests include deep learning, software for interpretability, and in particular, evaluation-centric explainable AI. With that, I'll hand it over to our speakers today.
Thank you, Shafat. I would just share my slides. Okay. Oh, I can currently not. There it is. Perfect. I hope you can all see the slides. And the slides are good now? Great. Okay. As already introduced, my name is Felina Bommer, and I am here today with my colleague Anna Hedstrom. We are both from UMI and we are very excited and honored to speak here at Climate Change AI. UMI originated at TU Berlin and then moved over to HEB Potsdam, where we are currently situated, and doing understandable machine intelligence research. Today we want to talk about Quantus X Climate, our tutorial submitted originally to ICLR last year. And we worked on this project together with Marlene Kretschmer as well as Professor Marine Höhne. This tutorial focuses on applying explainable AI evaluation in the field of climate science. And as you see, this is a very specific topic. So I want to start out by giving you a general motivation and then want to continue on to give you a general background on the topics related to our specific tutorial to move over to why we actually wanted this tutorial to happen and bring it out to you guys. And then I want to give it over to Anna, who is our expert on explainable AI evaluation. As we all know, global climate change has many impacts around the globe, two of which are the rise of weather and climate extremes, as well as the rise of natural disasters around the globe. You can see here a statistic on the left where the graph shows from 1980 to 2019 the increase of hydrological, meteorological, climatological, as well as geophysical natural disasters. These disasters cause not only big economical, but also humanitarian losses. This is why climate research has focused on improving forecasts as well as monitoring of climate and weather events. In order to achieve these improvements, there have been efforts to increase observation as well as data simulation. However, these new observation and simulation techniques come again with new challenges. You can see here a graph down below on the right where we have this cycle. On the one hand, we have the new ways of observing and simulating so-called big data, which comes with increased volume, velocity, variety, so different data sources, but still uncertainty, which are then fed into our evaluation procedures, which now need to facilitate big data. They need to be able to, in certain cases, be applied in real time since we have an increased data throughput. And we also need to integrate different data modalities, so to speak, but maintain confidence and robustness within these applications in order to gain knowledge that we can feed back and again improve our methods. In order to achieve that, AI methods, or specifically the super efficient deep learning methods, have become more and more important also in the field of earth science. This is here a graph from NASA published in 2020 where they show the percentage of published works discussing machine learning. And you can see especially in earth science here, the green graph, there has been a huge rise from 2015 to 2020. But not only the rise in percentage, but also successful examples such as GraphCast, which was published last year by Remy Lam et al., as well as ForecastNet, which was published in 2022, have shown that models exhibit increased computational performance while also providing us with comparable skill to existing physical models. Nonetheless, all of these methods come at the price of high model complexity, which makes them oftentimes black boxes and deems them untrustworthy and their results unreliable. In order to overcome this issue, the field of explainable AI offers methods in order to enable a deeper understanding of these deep learning or machine learning methods. In climate science, explainable AI can offer us three main advantages. The first one is model validation. I brought you here an example from recent research from 2021 where they use XAI for drought prediction. And here they have a combination of a CNN and a bi-LSTM, which does our drought predictions and then gets interpreted by an interpretation method. And they compare the interpretations to the different drought conditions and drought events. This enables them to compare the results also to physical evidence in order to check whether the physics learned by the network is actually valid. A second point is they can use then this information in order to improve the existing architecture. And also they can maybe gain from these interpretations new insights into physical knowledge that was picked up by the network that hasn't been yet examined properly. Although explainable AI offers many different advantages, the field itself is huge, and varied methods aim to achieve similar goals, such that in a research example, such as the drought prediction here, we need to make sure that we understand how the different methods work and what they actually try and achieve. So let me give you a quick overview over explainable AI. Little disclaimer, exact terminology varies widely within the field, but this here is our overview just to give you an impression. So we distinguish between two groups within the field of explainable AI. We have the post hoc methods and the anti-hoc methods. The anti-hoc methods can also be called self-explaining networks. Here we take network architectures and we adjust them to be more understandable. This can be done, for example, by introducing prototype layers where you have a classification task, and for each class you get a prototype to see what actually happens in the prediction. There's also such things as concept layers that work quite similarly, and also contrastive networks that kind of try and give you comparisons to make it more understandable how the network makes its decision. The second big group is the post hoc methods, which is what we focus on since they provide a little bit more flexibility as you don't have to adjust the network architecture. So they can be applied to already trained and existing architectures. And since we focus on that, I want to give you first a brief intuition of how these methods actually work. So what we usually have is a trained architecture, as I already said. Here in our example, this is contained within the gray box, where we have an input X that is fed to a trained network F that takes the input X and has some parameters, usually model weights theta, and then gives us an output Y. In our example, we have a yearly temperature map that is passed, for example, to a CNN, which classifies them according to the decade they belong to. So that would be the different classes. Now we have all of these information and can present it to the explanation method, which we here signified by the function phi, that then takes as input my input of the model, which is X, my trained model F, as well as the output, the prediction Y. Methods vary within what lambda actually signifies, so the hyperparameter of the method itself. One example is presented here that is a so-called attribution map. And in this attribution map case, each pixel is assigned a value according to the sensitivity that the model's prediction had towards this input pixel. And we call the explanation E, or describe it by the variable E. Within the field of post-hoc explanations, we also can distinguish methods according to different aspects. One aspect is the explanation target. So what is the explanation trying to explain? In local methods, we focus on the individual samples, trying to uncover how the prediction worked for each sample. In global methods, we focus more on the global aspects of the explanation. So, for example, we want to look how a whole class decision is working, or we can provide you with concepts for what individual neurons in the network have learned. The second aspect that we can distinguish methods by is the components that go into the explanation. So in model-aware procedures, we would be taking into consideration also information within the network architecture. So for example, gradients or even the model weights. Whereas in model agnostic procedures, these are more interested in the input and output and the predictive behavior rather than specific parameters from the model architecture. Lastly, we can distinguish in post-hoc methods according to how they present you as a user with the explanation, so the explanation output. There we have, for example, sensitivity methods, which would present you with a sensitivity value for each either input pixel or input feature of the network, according to how sensitive the network decision was to that pixel or feature. The second one is feature contributions, where each pixel or feature is assigned a contribution value according to how much it contributed to the network prediction. And lastly, we have the explanation methods that present you with an example. So they take examples from the training data and present you with examples that are similar or the same in prediction to the sample that you're trying to explain. As you see, this is very overwhelming and a lot already. And all of these methods have their own tweaks. So in order for us or the climate science field to be able to apply them, we have to be able to understand what different methods do and keep that in mind. This, alongside the increasing number within all of these subcategories that I just discussed with you, makes it super hard to choose the right or a suitable explanation method for a certain research task. So recent research has shown that in a user's case, we often end up picking an explanation method by popularity means, so what gets cited the most in our field, or upon easy access, so which toolboxes are available, and we just pick from them. You might ask yourself, well, why is that a problem? As I already said, these methods vary, and they are all based on the same goal. So they are all trying to approximate a decision process that is highly complex of a complex network. So they take their own route towards that goal. And what we end up with, if we go back to our example that I previously showed you, where I have the yearly temperature map, and I would try to explain it by different explanation methods, then I would end up with different, in this case, attribution maps for the same sample, making it very confusing to someone that doesn't have the huge amount of background knowledge about all of them, how to choose from them. And also, visual inspection of plots 1 to 4 are unintelligible because we don't know what's actually going on within the network. So if we think back to our research case, this could lead us to different explanation methods could lead to different conclusions, making model validation almost impossible at that point. This brings me to the open question. So how do we now evaluate and choose a specific XAI method for our purpose? With that, I want to hand over to Anna and hope that she can enlighten us all with the knowledge to that.
Okay, great. Thank you so much, Felina. Yes, so let's continue. So the question we could ask ourselves is how to measure and compare the performance of different explanation methods when we assume no ground truth. So just to rephrase what the challenge is here. So the challenge is what I refer to as the evaluation problem in explainable AI, and that is de facto lack of ground truth explanation labels. And this prevents us from using standard performance measures, such as computing explanation error. So what you see there is, again, the noise squared explanation, one of those local explanation methods that we computed on this task in the tutorial. We essentially make, if you will, a prediction of E, like the explanation, or estimation. And what we don't have is this kind of ground truth heat map to compare with. So there's no ability to compute this explanation error. Yet we still would like to know how to circumvent this very problem and make a judgment of the quality of phi. And so what we could imagine is that we have some function applied to phi, psi in this case, that generates quality estimates that indicate the quality of the explanation function phi. So we can continue. Right, so before just taking a look at what we have in the tutorial, I want to open up for a more broader view on how to estimate explanation quality. So you can think about this in the three options, if you will. So the first one would be to actually use humans. So humans can help us to evaluate explanation methods. Perhaps the question is posed a bit more differently, because you might ask, what is your preferred quality explanation rather than what is the correct one? But it is indeed a common practice within XAI research, especially in healthcare, and acts, I could say, complementary to metrics-based quality estimation. But I mean, a reasonable question to ask is whether or not we are able to be good judges of what a correct explanation is with all our cognitive biases. So I just inserted an image here, which is essentially on the left side, you have this input of an X-ray. So now we go to another application. Hope that's okay. And on the right side, we have an explanation output. So a GradCam explanation, a local explanation, attributes and importances to the different pixels. And here we have this area in red here that is assumingly important for the new phenomena prediction. So this kind of lung disease. But what we don't know by looking is why this is. So we don't know if it's about the airspace opacity, if it's the shape of the heart border, if it's the left artery. We just know that perhaps this area is important for the model decision. And we know that both trained scientists and healthcare professionals do indeed struggle with interpreting and trusting these explanations. And hence, you could ask if they are kind of perhaps questionable judges of explanation quality as a first step. So as a next step, what we could imagine doing as a kind of approach to evaluate or estimate explanation quality were to kind of look at what we have as ingredients in the evaluation function. So what about constraining some of the involved spaces, the kind of ingredients into this function, and then evaluate phi against some known or simulated ground truth? So what do we mean by that? So if we look at the first example, we can think about constraining the data space. So what do we mean by this? I can give an example. So for example, let's imagine we create this restricted data set that we can evaluate our explanation method against. So imagine you have a vision data set, for example, and in one particular class, you put in a white patch in the right corner. And only in one class you do this. Then you train a model. And then what you would do for evaluation were to say, okay, knowing that this model has access to only this feature, you would perhaps assume, but not guaranteed, of course, that the model used this white patch in order to make a prediction for this particular class as a feature. So what you could use is to do an intersection for other local explanation methods and say, do they indeed kind of assign explainable evidence to this white patch, for example, as a way to, and this is in this way we can restrict the data set and in this way evaluate explanation methods. As a second kind of approach, you can imagine restricting the model space, the F that we include. So imagine we say, okay, actually, we're not going to work with black box models at all. We're going to work with the models that we know how to interpret the coefficients, and the coefficients themselves work as explanations. So you can do some simple matching and say, okay, does my explanation method, this post hoc local explanation method, do they match the coefficients? So you can simply just eliminate the need for evaluation in the standard way, if you will. And as a third option, you can look at, thinking about restricting your explanation space or the explanation method that you use such that it satisfies some predefined axiomatic principles. So you can say, okay, while we don't know exactly how your explanation method work in practice, we can at least make some guarantees that in a nice in a nice predefined environment that explanation method would behave in certain ways. So let's move on to the third part. The third part is actually where we focus the tutorial on, and this is the approximation. So we estimate explanation quality by approximation. So in this area and these approaches, we already accept that there is no ground truth to be known or retrieved, and we instead measure fulfillment of desirable properties that we ourselves define, and this is what we can also call metric-based quality estimation. So for a couple of examples of this, we can imagine different properties that we want an explanation function to fulfill. So as a starter, we can think about wanting an explanation function or a method to be faithful to the model. So what we want to have is an explanation function that follow the predicted behavior of the model. So asserting that more important features actually played a larger role in the model decision. So how could we think about this? So this is a simple visualization that is basically kind of showcasing the principle. So imagine you have an explanation that highlighted certain part of the input. You then decide to take those that was the highest relevance, the highest attributions. You start to mask those first, and then what you like to see in the input, and then you would re-predict with your original model, and then what you hope to see is hopefully a decrease in kind of model let's say confidence, softmax output for that particular class. And this would then establish that there is indeed a relationship between the model and explanation function. As a second example, we can also imagine wanting our explanation function to be robust or like kind of mathematically stable. So what you could do is you could inject a little bit of noise to the input. So you have there in visualization, you have some kind of MINS, this classic toy data set, vision data set. You have this original input, and then you have the second row, which showcase a little bit of, I think is, Gaussian noise, white noise added to the input. And what you do in each of the different columns there is re-explain. So what you would hope for robustness is that if your model still predicted the same class with this additional noise, then the explanation output shouldn't be very different. So this is kind of the fundamental question you ask in the robustness criteria. And for the next one, randomization, it's thinking about kind of the opposite property, if you will. If you want your explanation function to be robust, that's great, but you also can imagine that you want an explanation function to be reactive to randomization. So what if you inject a lot of noise? Or what if you randomize your model parameters completely? How does the explanation look like there? So in this, for example, in this example, what you see here is a visualization of an evaluation metric that measures how the complexity of an explanation output changes when you have a random model versus your original model. And then we can continue. And localization is another property to look at. And then that is very similar to the idea that we explored together in the kind of restricting a data space. It's essentially where you have an understanding of, and essentially in segmentation mask or ground truth mask over your input. So usually in, for example, object detection, you have a segmentation mask that shows where the object is, and you might be able to use this for explanation to say, hey, did my explanation indeed assign kind of explainable evidence to this very area? So there's many variations of this. And also complexity is another one. You can imagine thinking about having explanations that are concise, that is preferable, that you don't want too many features in your input to be important, because then they might not be interpretable as a response. Okay. So Quantus. So what is Quantus? Quantus is essentially an open source Python library for explainable AI researchers, and it's done for allowing for evaluation of neural network explanations, and it's for machine learning practitioners. And it provides this metric-based implementation that we just went through, these different properties, that allows you to do experimentation. So here we have this image, and in part A, this is from the paper Quantus, that is also published in GMLR, and it's most importantly a software, living software. But on the A part there, you see this kind of, again, the motivation for why this is needed. So we also show this now in the kind of climate application, but here is an ImageNet classification task, and on the first column, and then you have different explanation methods. And again, you cannot really say so much about the quality of this different explanation method by just qualitative analysis. So with B and C there on the image, you see kind of illustrative examples, or examples where we have generated actual analysis for the quality over different criteria. So faithfulness and robustness and localization. And when we look at the library content, we provide around 35 metrics in 6 different categories, including tutorials and API reference. And when it comes to the data types, we support image. It started with an image classification kind of library, and then we have extended to time series and some tabular, and we're also working on extending it to NLP currently. It works also both with the PyTorch and TensorFlow, and it works with the feature importance methods. And again, this doesn't kind of limit them to only gradient or back propagation, model agnostic. It doesn't really matter kind of how you arrived at those feature importances. You can work with a kind of your custom own explanation methods you can benchmark with. But this is the limitations right now, but we're also working on potentially relaxing this requirement to allow for more free-form explanations. We also have some basic additional built-in XAI method support, so to get you going. So, but Quantus is indeed an evaluation library, not an explanation library. And applications so far, we have seen different ones, so in healthcare and XAI optimization and climate science and remote sensing, etc. Right, so we will go over this in the tutorial, but just want to showcase quickly how it looks like when you work with Quantus. So Quantus works with kind of evaluation works by one step, if you will. You first initialize, and you could then you make a call. So yeah, 1 or 2 steps. But essentially in the first initializations, you have Quantus.metric. So you decide, okay, what metric do I want to evaluate my explanation with? You also then put in your hyperparameters. So in this pixel flipping experiment, for example, we have to choose what we mask our pixels with. So here we chose black, for example, pixel color for the pixel masking. And then what we do after we have initialized this metric with the hyperparameters, we then call and evaluate the explanations. And here we have the same ingredients that we had in the psi evaluation function. So we have the model that we want to explain. We have the explanations in the A batch, or the attributions. We have the input and the labels, so X batch and Y batch. And we also have a little bit of plotting functionality. Great. Yeah, and if you would like to learn more, there is a paper, and of course try out the software and let me know how it works.
Yeah, I think we can now switch over to the tutorial. This is also, by the way, the link this project was based on. So the tutorial is actually based on a collaborative paper that is hopefully soon to be released in the AI for ES journal, and is currently also available on arXiv. There's also a corresponding GitHub repo if you want to reproduce paper results. So let me just quickly switch screens to basically over to the that's the tutorial. And yes, as I already said, this tutorial has been based on a publication. Maybe I need to make it full screen. I hope that works. Okay. So we have a lot of background information in this tutorial, also on what this is about. As we already discussed, it is basically to showcase you how to use XAI evaluation to select a method for your research case in climate science. And in this scenario, we have chosen a publication by Leib and Barnes from 2021 as our basically research example that shows XAI research in its active form. And here we build a or in this paper, they use a neural network in order to classify inputs, yearly temperature maps into their according decade class. And here we use a CNN. In the tutorial, we provide you guys with the pre-trained CNN as well as several input images, since we focus more on the explanation and then evaluation part. But to begin with, we explain a lot of the background information and how this impacts climate research. We also provide you with additional tutorials on Quantus, but we basically start with the simple imports. So we have the standard libraries from Python. We have plotting libraries and libraries to deal with data arrays, but we also import Quantus naturally, as well as Explain, since this tutorial is kept in TensorFlow. Yeah, here you can see all of the packages that are installed to keep it nice and reproducible and understandable what's going on. We first start off by describing what the data looks like. So this data comes from the Community Earth System model version 1 and is both the network and the data is available in a Kaggle dataset, which we also walk you through how to download these in the 3 steps, so to speak. And yeah, so basically this is the download setup, and then you download the data set which contains the following data objects, which we first go on to inspect. So what we have is the input data, we have the targets for the network, and we have the masks that we later on use for some of the evaluation metrics. And we have the years for each of the images that we provide you in the input data set, as well as latitude and longitude, since we are talking about climate maps. First, we look at some data points just to give you guys a reference. So what you see here is actually the yearly 2-meter 2-meter surface temperature maps for 1940, 1990. These are just examples to show you how the data looks like in the 2-dimensional plotting, basically. And here you can already see that it's the full globe, longitude and latitude wise. Then we go on to inspect the data, because basically what we assume is that the network will learn the global mean temperature trend throughout the data, as well as different local aspects within this, or local features on each map, to assign them back to their decade. So here you can see just the global mean temperature time series plotted to see that this exists, since this is simulation data of the worst scenario. I think it's RCP 8.5. The increase is quite strong. We also go and inspect the pre-trained model architecture that we provide you guys with. Here is a graph, and it's also very well described according to the publication that we released on arXiv already. And you can see which parameters were chosen for the network architecture. Here's also the graph. So then we just load the model from the downloaded data, we load the network parameters, and then we initialize the model according to the specific parameters that we have chosen. And then we do a prediction in order to show you guys what the output is. As I already said, this is a classification scenario. So we predict decade classes. And here you can see that the samples that we predicted leads to their correct classes. I mean, we chose them to lead to their correct classes. So here is the output. So this will be a one-hot encoded label. Yeah. Yes, then we continue by using Quantus as well as Explain to explain the predictions that we provide you guys with. So first here we look at the available methods in Quantus, seeing which methods are available for TensorFlow already built in. As Anna already mentioned, there's also a Captain library for PyTorch, not only TensorFlow. As Anna already mentioned, you can also write your own explanation function. We give a brief introduction on the individual methods, explanation methods, which you can read up here, and that describes basically how each of these methods calculate their explanations. We have 6 different explanation methods, some of which are gradient-based, others are contribution-based, and then we also have a model agnostic, so occlusion sensitivity method that does not use the gradients of the model. Then we go to the next step. We want to generate explanations for all of these 6 explanation methods. Here we have the code, how this works. So you just call Quantus explain, and then you pass on your model, you pass on the inputs, which is the X batch here, and the targets that you want to explain, and as well as the explanation methods that you want the explanations to be generated by. And if you run that over the whole number of explanation methods, you will get explanations per method. Here we always print the shape so that you understand. So we choose 4 samples out of the input batch, and then we have 95 by 144 is basically longitude by latitude. Then we go to plot the different explanations. As I've already shown you in the talk, pure visual inspection will be unhelpful to find out which one is great, but here you have them. So in the first row, we plot the input again, and then you have the according explanation maps, which for now just look very splotchy and unintelligible. We have some that might, on a first glance, seem to make more sense, but as we already know, visual inspection is not the way to go. All of these explanation methods are display absolute values. So the stronger the red, the higher the importance of the specific area. To give you guys a motivating example, and since we took the Leib and Barnes paper as a research case, we wanted to show you what could happen. So in this prediction scenario, one of the patches that is known to exhibit physical importance is the North Atlantic cooling patch, or so-called warming hole. This is a phenomenon that changes throughout climate change, and as always, will always throughout the decades be a very distinguishable feature. So if we go back, let me just quickly show it to you here as well. This is basically this first orangey patch from 1940 to 1990, and then it switches over to become the blue patch in 2040, and then the blue patch in 2074. So this is the feature we would look at in order to validate our model, because we think this is possibly something that the network could have learned or picked up on. So in order to address that, we want to check the explanations, or a usual way would be to check the explanations. So we again just plot for you guys the specific region, and then the same 6 explanation methods, and this would be a way to validate the model. But since we right now don't know which one of these are actually to be trusted, we need to continue with the evaluation part, which is where I again hand over to Anna.
Right. So thank you, Felina. Okay, so we have already gone through a little bit of the background of evaluation. Of course, we went over a lot of properties in a quick way. Here we try to reintroduce them, so we can continue down. I think, yes, so what we have here is simply just looking into what are the available metrics currently under the different categories. And of course, it's important to, when you apply them, just have a look at the original paper, because they are currently parameterized with the values that was introduced in the particular context of that particular paper. So it's important to always look into, does the parameters make sense for your data and model right now? So, okay, we can look into, just to understand how Quantus works, we start with one of the complexity measures, which is sparseness. And what you could do as a starter is to say, okay, I would like to know what hyperparameters or parameters are there. So we have this method get params. So then you see, for example, there is a couple of things, like you have the absolute and the normalize, which allows you to take absolute and normalize your attributions, your explanation methods, and then some particular ones related to the execution. So if you want to return aggregate results and so on and so forth. Right, but let's have a look. So the absolute easiest thing you could do to get started is just to initialize it. So initialize it with default parameters, so no changing any hyperparameters there, and then just adding all the different ingredients that you need. And we start by evaluating vanilla gradients. So here you would have one float per input sample. So here we just have 4 different samples just for illustration. But of course, you should run it on larger batches. Okay, let's imagine we want to change a few things. So we want to return aggregate results. You do that. You also want to disable the warning. Imagine you do this in a big loop or on a cluster, then perhaps you just would like to close down the warnings for a while. But they're also there for a reason. What we could do as well is then, okay, we have evaluated, so we got the value for like a sparseness value, where the higher the value, kind of the more sparse the explanation method is. So vanilla gradient has the value of 0.81. We might be interested in benchmarking it against some other method. And then you have the occlusion one, which has lower sparseness. And in this particular instance, then higher sparseness is desirable. Right, this was used to introduce the different metrics, how to run them. You can quantify different explanation methods. You can do simple, imagine like you take your dictionary of explanations and then you just iteratively compute the sparseness and print it. So there you have it over the 6 different explanation methods that we included in this tutorial. Right. Yes, so then perhaps more interesting and perhaps more valuable is to think about evaluation in a more holistic sense. So think about evaluating different properties. You can even imagine that these properties also have some trade-offs, right? Perhaps faithfulness and complexity might not be kind of fulfilled both at the same time. You might sometimes have to trade off different qualities of your explanation function. So it is indeed very interesting and important to look into different metrics and run the evaluation more holistically. So what we would do here, for example, is to say, okay, let's imagine we would like to evaluate these different properties, but there's obviously tons of different metrics to pick. But we decided to enumerate over them, and we did an analysis of what made sense in our particular case. So there is a follow-up work of this, which is called the meta-evaluation problem in Explainable AI, where we look into the specific problem of selecting evaluation methods. So sometimes, exactly, it could be helpful to use another analytical tool for it. But here in this examples, we went over them and selected those that make sense. So here we, for example, in localization, we decided to go for relevance rank accuracy and within complexity sparseness, but there are more options. Yes, so we run the benchmarking, which is also done similarly, just passing all the different ingredients that we need, the model and the labels and the inputs and the explanations. Or we decide, as we do here, a batch equal to none. So we don't pre-compute explanations, but we generate them within the evaluation. That's also possible with Quantus. Okay, we run it and we let it run for a while until it's done. And then as a result, we have some raw scores. We have these raw scores in front of us over different criteria in the columns, and then with the rows, we have the different explanation methods. We might need to post-process these because in some properties you might have like kind of the score direction is different. So in certain metrics you want higher values, and in others you want lower, etc. So what you do as an additional steps, perhaps before visualization, is to post-process these into rankings. So comparative look. So instead of looking at the actual scores, you want to say which one of those is highest ranked. So the highest quality versus lowest quality. And this is what you get in this view. Yes, and an alternative, let's say, view on that data frame would be to simply plot the rankings on a spider graph or radar plot. And this is the result. So where the further out the edges, the higher the performance. And you can then, by looking at the different colors and legends, follow along how the performance are on different explanation methods. And this is simply just to illustrate kind of the possibility with Quantus, what type of complementary analysis you can make to kind of visual analysis. Yes.
Yes, that already brings us to the end. We go on to discuss which explanation methods to choose. Let's say we take specific care about robustness as well as faithfulness and complexity. Then we would probably, as a trade-off, choose something like the integrated gradients method and then interpret the results. This can vary, and we then look again at the explanation maps. Okay, I think that brings us to the end. We also discussed limitations, but we're happy to take your questions now.
Thank you so much, Felina and Anna, for the wonderful presentation. We do have several questions from the audience. As a reminder, um, anyone that still wants to ask questions you can go onto the Slido link and keep asking your questions. So the first question is the paper mentioned on the choice of explainable method available as a preprint? I believe this was towards one of the last slides.
Yeah. I can also share the slides again if you give me 1 second. I just need to. Okay. Yes, I believe that was the slides you mentioned, right? Yes, it is available as a preprint. It is to be updated in the next 2 weeks, so look out for that, please, as well as the GitHub repository. And as I said, the reviewed version will be hopefully published soon. So we're on the last legs of the publishing process. So you can find it. This is the presentation. I don't know if we have any chance to give the links, but if you go to the tutorial, it is linked right at the top as an article, and you can just click on it and you get to the archive paper.
All right. The next question is, how can you choose the appropriate metrics to evaluate explainable AI methods?
Okay. Yeah, I mean, a very valid and relevant question in this context, given the kind of options that we have. I mean, we not only have a lot of options when it comes to explanation methods today, we also have a lot of options in terms of how we evaluate. And why do we have all these options? It's because we don't have the ground truth. So, you have uncertainty in the explanation space, and then you have uncertainty in the evaluation space. Like, how should the evaluation scores look like? Why do you have one explanation methods that get higher values than others, and so on, so forth? So it's a very relevant question. And there has been some kind of preliminary work into this, into, let's say, meta evaluating, so evaluating the evaluation method itself. And yeah, Feline and I, together with some other researchers, spent a little bit of time on this in the last year, and we have a paper related to this, and this is called Meta Quantus, so follow-up work of Quantus, essentially. And while we cannot really kind of look into the actual, let's say, accuracy or validity of the different evaluation methods, we look at their reliability. So through kind of verified perturbation, we analyze kind of the consistency of these metrics. Do they produce similar scores when you have a little bit of noise into the evaluation process, and the opposite? But yeah, have a look at the paper if you're curious. I can share it in the Zoom channel.
There's also a follow-up GitHub package, right, Anna? The Meta Quantus package. Yes. I can't hear anything.
Sorry about that. So the next question is, how can we know whether an explanation method qualifies for gaining insights into what other aspects might be causing a particular prediction?
Okay, I think there is no full answer to this question, but this paper is to raise awareness and to test towards the different properties that we have. So in a climate scenario where you might have or might be working with data that was coming from a simulation that has different ensemble members and will carry different variability, you want your explanation to be robust if the prediction stays the same with the sample that was inputted. So basically thinking about like choosing a bunch of metrics and then evaluating. On the other hand, I would still advise choosing or combining several explanation methods. If you go to the paper, that's also something that we, in the new release, will definitely put a very strong focus on to advise towards, because not all explanation methods will fulfill all requirements. So looking at it from different angles is always a good perspective, and I think it has already been done in some publications. I hope that answers the question. There was a second part to it. I think I forgot that one. Or was that already answered by me?
I think, yeah, I think
Okay.
you answered the whole question. Right. Is there a general best practice explanation method?
Anna, what would you say?
Right now, I don't think we sit with a better answer than it depends, and it certainly depends on certain like your ingredients into your like variable that you're like explaining. So whatever is the definition of F, and what is your data X, and what's your label Y if it's a supervised learning setting. So sure, there is definitely tools now to evaluate. You have this metrics-based evaluation that allows you to kind of get one step closer to the answer, at least sanity check. Do the explanation function, is it robust, is it faithful, etc. But I also think that we are definitely there's more steps to be done in terms of looking into all the benefits with other approaches, like, you know, for example, like evaluation by restriction has its certain pros and cons. Evaluation by approximation has its certain pros and cons. And it really kind of remains to investigate and research about how we can combine kind of these all approaches, and so come one step to the answer, which explanation method should be chosen. So the answer is, it depends.
Yeah.
I
think we are, yeah. I think we are very far from one size fits all explanation methods. Yeah, as I said, maybe taking several is a good answer towards this, and also taking a global versus a local look, aggregating all of these different steps that you can take, and just Quantus just helps you figuring out what your explanation method can and can't solve.
How easy is it to add another XAI method to Quantus? For example, SHAP. Does Quantus work with PyTorch models? Does it work with PyTorch Lightning?
Yeah, so the first question is how easy it is to add your explanation method. So you do not have to add kind of a specific explanation method into the library itself. Like, you don't have to create a PR and then get it merged and write tests. You can simply just write your own Python function. So what it has to have is follow the same signature. So have this kind of model, inputs, targets, and then quarks, which is essentially kind of the ingredients, and then return a numpy array. That's kind of the expectation, and there is documentation for how to do this, but it should be simple to evaluate your kind of custom made explanation method. And yes, the kind of yes, so Quantus works with kind of torch and then module type models, so it should definitely work in the case prescribed. Yeah.
Yeah, and to PyTorch Lightning, just because I recently worked with that, you can just merge back to, if you have a trained model, you can generate a normal PyTorch model from the Lightning version. So it is backtrackable again to Quantus. You can just apply it if you just go back to the normal PyTorch version from PyTorch Lightning, and then you are good to go.
I think that's all the questions we had for today. Thank you once again, Felina and Anna, for the amazing presentation. Thanks everyone for joining. Our next webinar will be in 3 weeks in March. It will be focused on climate finance and AI. We look forward to having you all attend that webinar as well. Thank you.
Thank you.
Thank you so much.